All right, physics. We're going to talk today about springs. So let me pull up this handout here, and hopefully you've already watched the video, and you picked up from the video a couple of the equations that we're going to use with springs. I'm going to go ahead and kind of write these at the top so we have them to work with on this handout. And I'm going to work a couple problems with you. First equation is the force of the spring when we compress or stretch a spring is negative kx. And it is okay for now. We're going to kind of, for the most part, we'll just drop the negative. What you need to understand about the negative sign is, like it mentioned in the video, it's a restorative force. The spring always wants to go back to its neutral position. And so the force, whether you stretch the spring and it goes back, or whether you compress the spring and it goes back, you actually have a negative force in there. That's where that negative comes from. We will pretty much, for the most part, just kind of ignore that. The K has to do with the spring constant. It basically tells you how many newtons of force is needed to stretch the spring per meter you stretch it or compress it. And the other equation, I'm going to just use E of S, energy of the spring. That's the stored energy is equal to 1/2 kx squared. The x has to do with how much you're displacing or compressing / stretching the spring. Okay. All right. So here's the first question. We have a 4 kilogram block. It's compressed against the spring and it's released. The block slides on a frictionless surface. The spring was compressed a total of 12 centimeters. So that's what we're going to use for our x value. And it says the maximum force on the spring. That's what we're going to use. The force of our spring is 16 newtons. So the first question here is, as we sort of push against and compress that spring, what is going to be the force of the spring as it compares to the K value? So the force of the spring is equal to K times X. We're going to drop the negative sign. Don't really spend a lot of time worrying about it. We know that the force on the spring is going to be 16 newtons, right? The K value is our unknown, the spring constant, and the amount that the spring is compressed or stretched, in this case we're compressing, is 12 centimeters. Now be careful with this. This has to get converted to meters. So we're going to go with 0.120 meters. To get K by itself, I'm going to divide both sides by this 0.120 meters. 0.120 meters. That's going to cancel. And then we get a K value of, punch this into a calculator, 16 divided by 0.120. We're going to go 3 sig figs. 133 is what the calculator tells us. And this is newtons over meters. Again, what does that mean? If I want to stretch the spring or compress the spring a full meter, I need 133 newtons of force. That's what the spring constant is. How much energy is stored in the spring at that point? Well, here's our equation. Energy of the spring is equal to 1/2 times K times X squared. Obviously, the more we stretch or compress the spring, the more energy is going to be stored. So we just put in our numbers, 1/2 times this 133 newtons per meter we just found, and the fact that we are compressing it 0.120 meters, we have to square that term. So when you punch this into a calculator, 0.120 squared times 133 times 0.5, that gives us, we're going to go, looks like 3 sig figs here, 0.958 joules of energy. Okay. Now, we're still talking conservation of energy. So the question is, when that spring is released and that box goes that direction, the question is, how fast will that object be moving as it leaves the spring? So we kind of make the assumption here that all of this spring energy gets converted to kinetic energy. Well, we know that amount of energy. That amount of energy is 0.958 joules of energy. And if we set that equal to our formula for kinetic energy, 1/2 mv squared, then we should be able to come up with the velocity. So we're going to do 0.958 is equal to 1/2 times the mass, which is 4 kilograms, times v squared. We've done this several times. 1/2 of 4 is 2. So I'm going to take my 0.958 divided by 2, because that's half of 4, right? That gives me 479. And then I'm going to hit my square root button or go to the 0.5 power. And that's going to give me a velocity of 0.692 meters per second. That's the velocity that that object would leave the spring. Okay. Let's move on to question 2. I'm going to do question 2 with you. It says we have a ramp at an angle of 28 degrees, spring constant 636 newtons per meter, and it's going to basically, as the block leaves, it's going to go up the ramp, right? So first thing we're supposed to calculate here is we're going to calculate the maximum force that the spring exerts on the block. So when that spring is compressed, the force of the spring is going to be equal to, we're going to go Kx. Remember, we're not going to worry about the negative sign there. So to get the force of the spring, we're going to take our K value, which is 636. We're going to multiply by the amount the spring is compressed, which again, we have to use meters. So we're going to go with 0.111 meters. And you multiply those two together, 636 times 0.111, you're going to get 70.6 newtons. That's how much force that the spring is now going to have when the spring lets go. So the question is, what's the velocity of the block after it separates from the spring? Well, we have to do a calculation here. The first thing we have to do is we have to figure out how much energy is stored in the spring. And we do energy is equal to 1/2 kx squared. The energy of the spring is equal to 1/2 times 636 times 0.111 squared. So we're going to take that value, 0.111 squared times 636 times 0.5. And we find that there's 3.92 joules of energy stored in that spring right before it lets go. What's going to happen? All of that spring energy gets converted to kinetic energy, and then we can set that equal to 1/2 mv squared. So we're going to take our 3.92 is equal to 1/2 times, let's look at the mass of the block, 0.838 kilograms, right? Because it says 838 grams. We're finding V again, so it's the same idea. We're going to take our 3.92, divide by half of 0.838. So what I'm going to do is take 3.92 divided by 0.5, which is a half, and then I'm going to hit divided by 0.838 again. That gives me a 9.35, and then I hit the square root button. My velocity ends up being 3.06 meters per second. So all of that energy from the spring that's stored gets converted to kinetic energy, and then we can calculate what would the velocity of that be. Now, think about what's happening here. As the block has its kinetic energy, it's going to go up the ramp. It's going to convert this kinetic energy is going to turn into gravitational potential energy. So if I want to know how high this way it's going to go up the ramp, all I have to do is set this equal to mgh. So go back and we already know how much energy, 3.92 joules, set it equal to the mass of the block, which is 0.838 kilograms times 9.80 times h. So 3.92 divided by 0.838 divided by 9.80, we get an h value, a height of 0.477 meters. And we talked about this before, whether or not it's launched straight up or it goes up the ramp, the block is still going to convert all of its kinetic energy into gravitational potential energy. So whether we treat it up the ramp or just straight up, it makes no difference. That h value is still going to be the same thing. Okay. All right. I'm going to do one more problem with you. And this problem actually looks very similar to one of the ones I just wrote for the test. So make sure you're paying attention to question 3. It says a spring is used to launch a ball vertically. The spring is compressed 4.5 centimeters and is launched, it's hard to see, the 1.23 kilograms. Let me get rid of that for a second to make sure I get all the data. We're going to launch it to a height of 0.88 meters. Okay. So first thing it's asking us to do is let's calculate the gravitational potential energy at its highest point. Okay. So I want to know, once the spring launches this ball vertically, how much energy will it have? Okay. I actually don't need the zero in there. I'm just going to find out this MGH. So I plug in my numbers. I know that the mass is 1.23 kilograms. I know that 9.80, and then our height that it launches is 0.88 meters. So when I plug all this in, 1.23 times 9.80 times 0.88, I get, and I probably should go, let's keep it 3 sig figs. So I realize my 0.88 is really only 2, but I'm going to call this 10.6 joules of energy. That's how much energy it has at the highest point in terms of gravitational potential energy. The question is, part B, it says, assuming all the energy was conserved from the spring, determine the spring's constant. So here's what we're saying is that the gravitational potential energy at its highest point was equal to the spring energy that launched it in the air. Well, we know that the spring energy is 1/2 times kx squared. So what I need to do is I need to set my 10.6 equal to 1/2 times k, which is our unknown, times how much we compress the spring. Be careful, it's 4.5 centimeters, so it's 0.045 meters. And that is going to be a squared term. So I'm going to basically say 10.6 is equal to 1/2 times k times this term here is 0.045 squared. That gives me 0.002025. I'm not paying attention to sig figs yet. I'm going to divide both sides by 1/2 and 0.002025. So that on the right side, that cancels, that cancels. I only have k left over. So I'm going to take 10.6 divided by 0.5 divided by 0.002025. And I should get an answer of a big number here, k. I'm going to go 3 sig figs, 10,500 units are going to be newtons per meter. What does that really mean to us? That means if I wanted to stretch that spring or compress the spring a full meter in displacement, it's going to take 10,500 newtons of force to do that. All right, you're on your own on 4. I really think the way this one's set up, I think it's kind of a fun problem. Follow part by part. I think you can get through it. I will probably post an answer key on this. So good